think we are set. Hello. Okay. Let's start. Okay. Welcome you all. So I am Shanmuga. Some of you may be aware and through the website. And I'm a faculty in electrical and computer science at IIT Gandhinagar. So I roughly work in the areas of computer vision and graphics. And so there are 3 sessions I will be taking. So now 2 p.m. Today, and I think around 11 a.m. tomorrow, and then again 2 p.m. tomorrow. So what we are going to do is we are going to use this session today as a preparatory session for you to understand the advanced concepts we will be discussing in tomorrow's sessions. Okay, so because I don't know about, you may have come from various background and you may not everyone be aware of all the computer vision things. So what I'm going to do is I'm going to talk about a brief tour of computer vision, right? So what is computer vision and how the field evolved and what is its relation to other areas and how the algorithms are developed and how the recent evolution of deep learning has resulted in some changes in the way computer vision is being done. Okay, so that's a thing we are going to see in today's lecture, and tomorrow onwards I'm going to go into the specifics and tell you some of the developments in the last 7-8 years or so. Is it fine? So let's go ahead. So let me first ask with a very basic question. So let's try to understand. There are 3 related terms, right? So there is something called image or video processing. There is another term called, the second term, I will leave out some space. The second term is something called computer graphics. And third one is the computer vision. So before we proceed further, we will just see through some examples and some basic concepts. So what are these 3 terms, right? So this image or video processing, computer graphics, and computer vision. Okay. So let's draw some blocks. Let me draw one block. So this is the image or video processing module. This is the computer graphics module, and this is a computer vision module. Okay, so every system takes something as input and something as output. Let's mark them. Also this system. Okay, so anyone has any idea? So I will mark it I/video processing module. This is computer graphics module. This is computer vision module. So you have mics? Yeah. Okay. So anyone wants to say what is input and output? We'll go one by one. So what is the input and output for a image or video processing module? Image or video as the input, and output image or video. Okay, so those problems, those class of problems we call as image or video processing problems. So it takes an image or video as input and outputs an image or video. So can someone tell some examples of this problem, like class of problems, image or video processing problems? Finding it, that's not that output is not an image, right? It is detecting and it is detecting whether a person is present or not. So it falls into a later category. Okay, so image should go in, image should out, come out, right? Yeah. Yeah, so you can say photo editing. So photo editing could comprise of many things. So one is you can, if the image is noisy, you can remove the noise from the image or video, right? So there are also noisy image or video goes as input, and noisy and denoised image or video comes as output, right? So something else, let me tell. So the compression, right? So you have uncompressed video or image. So you have standards like JPEG, MPEG, which uses them and compress them to another like low storage occupying image or video. Any other thing? Any other applications you can think of? Any other? Any other application? Anyone? Okay, yeah. So something like, yeah. So something like that problem is belongs to a class of problems called image compositing problems, where you remove one background and put another background. So input is an image and you get an image with another background as the output, right? So these are some of the things. So now you get a rough idea, the class of problems we are going to talk about. So because the applications we are going to discuss in tomorrow's sessions will be one of them. So one among them or something related to them. So that's why I wanted to discuss. So let's go to the next thing, computer graphics. So what is the input and what is the output? Equations. Yeah, you are close. Yeah. Yeah, so you can say some attributes of the scene as the input, right? So you give some rules or attributes as input, and finally the computer graphic system is going to output you an image or a video. Okay, the output is like the previous thing. So this process is traditionally called as rendering, the real-time rendering and other things. So where image or video is the output. So you want to generate animated movies, for example, right? So you need to give some rules or attributes. So how the objects associates, right? And what actions are happening. All those things come in the attributes, right? And who are the characters present, who should be in the final image or video. So all those rules you need to define, right? And finally, it will give you an image or video, right? So what are the examples? So one of the things I told is real-time rendering, which is used for CG effects, which have these characters and everything. And any other thing which you can say it's a computer graphics. So it's for animation, right? So the real-time rendering for animation and everything. So any other example? Any other example where you give the rules or attributes and CG? So
3D modeling.
3D modeling. 3D modeling. Yeah. So for an example, you give the coordinates of the points and you create a 3D this thing, right? So virtual 3D generation. So that could be one of the graphics things. So you create a virtual 3D. There is no real thing, but you give the positions and this thing, and it renders a 3D scene for you. Any other? Transformation in the sense? What is the translation? Translation, it's in text, right? So sharing, okay, but you need to have an image. So so translation would work given that you want a coordinates are some circle is some circle with radius this much, and you want to create this thing. So any geometric shape render this thing, right? So geometric shapes synthesis. So you give the equations someone told correctly. So you give the equations and everything, where they are located, how much they are translated, relative shapes are translated, and so on. What are the types of geometric shapes present? So those things you give, and so now you get an idea, right? So these are the class of problems in the computer graphics. So let's come to computer vision. So what is the input and what is the output? Anyone? Yeah, input would be image or video. That's correct. Is correct. Yeah, that's correct. So you need to just invert the input and output from CG. So here it's so you can say some attributes, right? So someone remarked face recognition. Okay. So suppose you give image or video and ask your system to output who are the people in the image or video. So face recognition is one such example. So someone told earlier. Any other thing you can think of? Object detection, yeah. So you put a bounding box around the object given an image or video. That's fine. Anything else? Emotion recognition, yeah. So in general, we can mark it as a class of action recognition. Okay, so this emotion is also different actions through the facial images you can recognize, right? So given an image with the person having some emotion, so you can see what action he's performing. So through video, you can say action recognition. With a given an image, you can also have an emotion recognition as a separate topic. So we can mark it. So any recognition task is a computer vision task. So emotion recognition from an image or action recognition from a video. So emotion recognition could be through video input also. It's fine. So any other things? OCR, yeah, OCR, which is that thing we are going to see in tomorrow's lecture. There is this data set, the famous data set, MNIST data set for just numbers, and there are different languages, different data sets are there. You give an image of the some handwritten text, and you want to recognize or convert it into the actual text, right? So that, yeah. Any type of recognition is a computer vision task. Yeah, that's true. So that's why this should go end to end. So suppose you want to get the attributes through the computer vision system, you want to change the attributes to something else, and then resynthesize the image or video. So you should have something like this image or video to image or video kind of thing, right? So the typical computer vision task, the classical sense, only image or video is the input and attributes are the output. But even in present scenario, after this deep learning, there are two types of models you can have with deep learning systems. One is inference kind of thing, which is the recognition is one of the tasks. Or you could also do synthesis tasks, generative tasks, right? So generative task, or you can do an inference task. So inference task is the classical computer vision problems. The generative task would involve some kind of graphics. So the fields are a bit blurred after the deep learning came. So even the generative tasks, people call it computer vision. But in a like traditional sense, so this is how these look. Okay, everyone clear with this? So let's then move on and talk about some background of classical computer vision. So I'll give some idea. So what are the two things? So before this deep learning, machine learning came, so what are the two things using which, on which this computer vision problems were solved? So two or say two or three tools. So can anyone tell me? Those are softwares actually. So I'm telling mathematical tools are something you want to solve. So before you code, you need to form the solution using some tools, right? Mathematical concepts or frameworks using which people used to solve. Anyone has any idea? Matrices, yeah, linear algebra they use. So that's at a very low level. So in general, I can write the tools I will explain. So the one tool they were using. So this is very primitive tool. Matrices are used everywhere. So I'm going to divide it in terms of the fields on which. So the signal processing is one area which people use. So they consider these images as signals and then try to apply signal processing concepts to solve these problems in computer vision. Right? So the next one is optimization. People used to do continuous, discrete, all these optimization methods to minimize a cost function and do all those things. So some of the things you may be doing even locally in a deep network, but global optimization schemes were very much used and large scale optimization techniques were used to do that, right? And the third one, the main important thing is the fundamental difference is the classical computation rests on understanding the underlying geometry. So geometry of the scene was quite crucial in finding solutions of most of the problems. That means where the camera was positioned and where the scene was, right? And if there are multiple cameras, what are the relative placements of those cameras and how the same scene got imaged by the different cameras and so on. So we are going to discuss in much detail. Okay, so this one is the concept of geometry. Okay, so especially there is a class of geometry called projective geometry, which people used. So this optimization you might have already seen during the lectures earlier, so I'm not going to spend a lot of time, right? So one particular thing from signal processing, which is common both in the classical computer vision as well as what came afterwards, which is the deep learning. One field of deep learning is the convolutional neural networks, right? So the one thing which was quite used, so any vision system used was some kind of filters. Okay, so you have an image or video, you want to get the information useful to you. So the scene may have different things, right? So you want to process it to get the basic information necessary to you. So you needed to use some 2D filters or kernels, right? And with the original image or video, you had to do the same operation as a convolutional neural network does, which is the convolution operation. Okay, so the signal processing, the main operation involved was convolution. Okay, and in the geometry, there are three major things I can say, right? Three major tools which were used. So one is, what is the relation between 2D and 3D? So image is a 2D quantity, right? But the actual scene is a 3D, right? So how the 3D point, any 3D point got projected onto your 2D image? Everyone got it? So there someone told about matrices. So all the analysis we do in this projective geometry are using matrices. Most of them are using matrices. Okay, so we are going to discuss in detail about a particular matrix which is called a camera matrix, right? Which is going to map every 3D point into its 2D location in the image. Okay, so the three things which are useful in the projective geometry sense are the camera matrix. The first one is the camera matrix. The second one is, so camera matrix is for one scene is there, one camera is there. What is the relation? That is the camera matrix, right? So suppose the same scene got imaged by two cameras, like our human eye, right? So two eyes act like two cameras. So you can do an experiment also, like this is called a stereo setup. Right, so you have two eyes seeing the same scene, and there is some kind of processing done in the brain which gives you the 3D perception. Right, so you can do an experiment like trying to put a thread into a needle, for an example, closing one eye. Very difficult compared to having the two eyes open. This is a simple experiment you can do to realize the importance of having a 3D vision, to stereo vision to get the 3D perception. right? So people started developing theory behind images which are captured by two cameras of the same scene. Or they also in parallel try to get an association between two images of the scene through some matrices. Okay, so this class of geometry is called epipolar geometry. And the third class, right? So then people wanted to extend it to n cameras. So an array of camera. You imagine a setup where some paparazzi have a lot of cameras and someone walks in, everyone clicks the photograph. So what is the relation between images captured through all those paparazzi cameras, for an example? Right? It's a practical scenario in which. So there is a theory which governs it. So for an example, this theory was used earlier before this learning-based things came to even reconstruct a monument. The 3D modeling of a monument they could do by just mining the internet photos. So different travelers went and took the photo of the monument from different positions, and all those photos could be mined, and they could use the theory of structure from motion. Okay, it's called structure from motion because there is a relative motion between different things, and you are recovering the structure from it. The relative positions of the cameras, each camera is in motion with respect to the other camera, right? So this is the structure from motion. Okay, and this one is two cameras, and this is for n greater than 2 cameras. Okay, and all these problems which I all the things I told, like they are sometimes called a low level vision problems or mid level vision problems, because still you are not going into estimating the true vision things. So what are present in the scene and everything. The depth is the main concern for us in this epipolar geometry, structure from motion and everything. But the theories developed for this could be applied to other problems, right? The primary thing is you recover the depth. So finally, you will have image as the input, which is a 2D data, and a 3D data is coming out. So this is like a image processing setup we saw. But this is class of computation problem because you are adding one more attribute. Yes, there were only 2 dimensions which were going in, but a third dimension is coming out, which is the depth. So, and another class of people, the fourth one I just mentioned, I don't know, I'll have time to discuss it. That is the photometry based methods. So everyone, like all these problems, if you see, you can go back in time, and there is a famous scientist from MIT who is called David Marr. He wrote a book called Vision. So most of the problems, classical problems of vision, were derived from his book and his research earlier done. Okay, this photometry based problems, what they tell is the geometry, understanding the entire projective geometry is not important. So how the intensity variation is there in the given image or images, you try to get the depth, right? Photometry or radiometry based. So in this, what happens is there are some problems. I will give some examples. There is some problem called shape from shading. So the example, simplest example you can imagine is you have a ball. This works mainly for some proper geometric objects. So you have a ball, you shine the light from the front, for an example. What will happen? The light will be very much at the center, and then it will diffuse kind of thing, right? So by measuring the intensity variation, you can get a structure of the ball, right? So from the image, how the intensity is varying as you move away from the center. So that gives some kind of a 3D information. The shape from shading algorithms are based on that. And there is another thing called photometric stereo. Okay. So here, instead of, so in the stereo problem, this epipolar geometry, which is the 2 cameras is the stereo problem, their cameras are at different locations, like our human eye. So this eye is physically at a different 3D location compared to this eye. So in the photometric stereo kind of problem, what we do, we have a scene, the camera is fixed, scene is also static. So you change the lighting. So you illuminate the scene, right? Some way, take an image and then change the illumination. For an example, I have lights. So I take an image. If I want to take another photo, I switch off 1/3 of the lights, take another photo, right? Another time I want to take an image, I switch off 2/3 of those lights and take another photo. So I have 3 photos. So 3 or more photos are required in this class of problems, where in classical setting, if you want to solve, you can get the 3D information of the scene. Yes. Okay. So these are this thing involved. So how many of you are familiar with convolution? Raise your hands. Okay. Some of you are not aware. Okay. So I'll give you a brief tour of convolution, which you would be using it extensively in the understanding the convolutional neural network later on. Okay. So let's start with convolution. Before that, I want to suggest some reading material. If you want to understand the topics which we are discussing, the first book would be Computer Vision. So this is a free book which is available on the internet. You can Google and download by Richard Seliski. The latest edition is available. So you could download the book and read it. Okay. So Computer Vision Algorithms and Applications by Richard Seliski. So it's a totally up to date. Few months back only the latest edition came, so you could refer that. So the earlier edition had mostly classical methods. Now the latest edition has both the classical and the learning based methods. The second book, you can, if you want to understand this deep learning, is another free book called Dive into Deep Learning. It's a good book. So it has all the codes also available, and there are some courses, and many universities have adapted it. So I think by Smola and others. Okay, so many authors are there. So this is also a free book. You can directly use it. Okay, and the third one, which I would suggest, is the code on this Python, PyTorch, or TensorFlow. Everything is given in this book. So the third one is not a free book, but we will be using very good, very much, is another book called Deep Learning, a Visual Approach. It's not a free book, but all the images of the book and the complete codes of all the examples in the book are available to you. By Andrew Glasner. So this is also a very recent book. It's it released, I think, some 8 or 9 months before. So this book is quite good, and you can, if you find spare time, you can work with these codes also. So you can Google and go to the book's GitHub page and use it. These 3 books should be sufficient for most of the topics which we'll be discussing. All are updated books. Okay, so they cover all the recent advances in vision, like transformers and variational autoencoders and all those recent concepts in deep learning, which could be applied for computer vision problems. Okay, and yeah, so there we stop. Let me go here. So let's talk about convolution. Okay, so there are 2 types of convolution. So we don't have to understand that continuous convolution, which is because continuous convolution, it requires you to sample data at uncountably infinite number of points. But when you want to do convolution in your digital devices, like your computers and GPUs, so you need to discretize it. So the continuous convolution is the convolution which happens in the real world, but for our understanding, we are going to approximate it using a discrete convolution and then adopt it. Okay, So let me call it discrete convolution. Okay. So let me take an example to make you understand this. So let's say some people in electrical background call it signal, and some people call it a sequence. Okay. So let's do in 1D first. So traditionally in the convolution, if you want to convolve two sequences or two signals in discrete thing, so what you have to do is you have to keep one signal as it is, another signal you need to flip and then move across the other signal, right? So that's a conventional convolution. But in the convolution, in the image processing and also in the deep learning sense, what we are going to do is some operation called correlation and call it convolution. Okay? So we are never going to flip it. That is the first rule you need to understand, right? You will just use something is there, you will just move across the other thing. So two sequences are there, you will move across this. So tell me one thing, very basic question. Suppose I call the first one as x1 of n, which is of length n1, right? So the length of this first sequence is n1, and x2 of n is the second sequence, which is of length n2. Okay. Suppose you want to do convolution of these two and get another sequence. So the symbol we normally use, y of n, is x of 1, x1 of n convolved with x2 of n. So let's extrapolate it to 2D later on. It's easier to understand in 1D first. Okay. So we write like this. So this is a symbolic notation, but actually what is happening is summation over some dummy variable k, x1 of k, x2 of n minus k. So this is what is happening. Okay, this y of n. So let us understand this equation. So this will give you this thing. So this equation looks pretty complicated to see this, but if you look at it, there are two sequences again created inside. One is x1 of k, another is x2 of n minus k. So another sequence was created by flipping and shifting, right? So, but I told this flipping is a bit of a complicated procedure. We don't want to always consider this flipping thing. This minus k we don't want to do. Okay. So actually what we are going to do in deep learning and everything is always do plus k. Okay. So we are going to just to keep either in 2D or 1D. So some input data is their image. So some other filter we are going to keep and move it around. Okay. So we can write it also as, so now it is plus k. Now I can easily write this as an inner product between one sequence x1 of k and another sequence x2 of n plus k. Okay. This is actually a correlation. Okay. So, but we will call it convolution as per the common nomenclature. So can I write like this also? Anyone has any concern? Can I write like this? x1 of k inner product with another sequence. So one inner product I take after a shift n, I am going to get one number. So I have a sequence, I have a shifted sequence, I take an inner product, and we are going to put it at the location n in the new sequence y you are creating, right? So given a thing of length n1 and another sequence of length n2, so what would be the length of y of n? So when I will exhaust the one sequence I am fixing, another sequence, so wherever it is, I'm going to move this side and this side to span the entire length of the other sequence, take that many inner products. So that how many inner products you are going to take is going to determine what is the length of the output sequence y of n. Everyone understood? Okay. How many ever inner products I am going to take, that much will be the output y of n. So how many inner products? So let's take an example. Let this, without example, it may look this thing. So let me mark the indices 0, 1, 2, 3, 4, 5, 6, right? Always we index the sequence using integers. Then let me write down x1 of n and x2 of n. Okay, or in other words, in our dummy notation, we will write it as k. So n is the shift we are going to do. So I'm using k for this thing. So n is the shift we are going to make on the x2 of k, right? According to the equation. So now let me put some random values 3, 4, 5, 1, 3. This is this thing. And this one is going to have 2, 1, 3, that much. So now not go out of this. So now if you see this, the n is the shift, right? So n, if it is positive, that means which direction you will move, which direction you will push this x2 of k. N is positive means to the right or to the left? To the right. Everyone agrees? And if n is negative, we will move to the left. Everyone agrees? So this y of n, so this y of n can have the index both positive and negative, because if you shift this side also, there is some finite inner product you are getting. So as it is, you take inner product of x1 of k and x2 of k. So at 0, what is the value of the output sequence? You will get it. Yes. So what is the inner product as it is? Other things are 0. Okay. So all the other things. So whatever I mentioned only is there. So all the other things are 0. This 5 and 6 I will remove. So the length of this sequence is 5. This is 3. Okay. N1 is 5 and N2 is 3. So what is the value of y of n at 0 shift? 25. 6, yeah, 25. That we'll write down. Okay. So now you shift it to we'll first push it to the left. So for that, what you need to do? -1 you need to put, right? -1, it will entire sequence will shift to the left, right? So what will happen? So this 3 will get multiplied by this, and this 1 will get multiplied by this 3, and 2 will be multiplied with 0. We don't care, the inner product. So this inner product I'm talking about, right? At the index -1, what is the value you will get? 12 plus 3, 15. Fine. I make some error, someone point me. Then one more shift we can do. Still we can have some overlap, right? So what you will do? So you make shift by -2. So then you will get the value of y of n at -2. What much? How much is it? 9. So after that we are now getting 0. So we don't have to. Then let's go back to this original configuration and start pushing this sequence to the right. Right? Then what happens? Then what happens? So then you push it to the right. Then this gets multiplied by this. This gets multiplied. This gets multiplied. 3 plus 5 plus 6. The 8. 3 plus 5 plus 8. How much? 16. So at 1, you will have 16. Everyone agrees? Then we push this guy this side by 2. So you will get the value of y of n at 2. Okay. Then what will happen? Then yeah, so 2 means this will multiply this will multiply this, and this will multiply 10 plus 1 plus 9, 20. then 3 push, then what will happen? This will not multiply anything because it went out. This guy will multiply this and this will multiply this. That's all. How much? 3 plus 2, 5. And you push now by 4. Then what will happen? Only 2 will multiply this 3, 6. Okay. So what is the length of this? 7, right? 7. So what is the relation of the original sequence and the final sequence? N1 plus N2 minus 1. Okay. So if you have two sequences of length in general, N1 and N2, this will have N1 plus N2 minus 1. This is the first thing you need to understand. Okay. Is it fine? And now this is for 1D, right? So this is used, this kind of convolution is used for analyzing some speech or any ECG and those kind of thing. You need a 1D filter to move around. So what is the use of this filter, I will say. So normally we call the bigger one here as the signal or the data you want to process, and this is the filter coefficient. Okay. So now let's write down the equation for 2D convolution. Here you have two signals, x1, which is m comma n, and x2, which is m comma n. Two signals we want to convolve, and this y of m comma n is equal to, if you want to write down, then we will write k1, k2, two dummy variables will put x1 of k1 comma k2, x2 of m plus k1 comma n plus k2. This is also 2D correlation, but we call it convolution. So here what happened? There was a sequence on which you moved only in one direction. Here each of them is a two-dimensional thing. Each of them is a matrix. In a 2D case, each of them is a matrix, right? So how you can visualize this? I'm not going to do a numerical example. It will take a lot of time. So just this concept you are clear, then it's fine. So now let's take this x1 of this thing. Okay. So let me call this x1 of k1 comma k2. Then the other one, this guy, let me draw with a different color. This one, a smaller one, is the filter, is this square. This one is x2 of m plus k1 comma n plus k2. So what you will do here? So there you moved in only one direction. Here you will place it first at the top corner, right? And some padding is required actually. So I'll come to it when we require. So if you want the output to be the same size as the input, because there is some reduction happening as we saw. So that need to be compensated, then you need to do some zero padding or some padding on the edges, right? So to filter the corner things, because we assumed it. So here we will not assume it. We will leave it at that. So what you have to do as a conceptual level, you will just move it around. So you'll first keep this filter here. Whichever is the center, we will have that, right? So and then take the inner product and put it at the center. So what will happen is if you want to keep this only within this boundary, then what will happen is the output will be some this by 2 amount, this width by 2 amount less than the original thing, because you have not filtered this. So what we will assume is this has some padding which with zeros, and then you can give an image, and then you place this 2D filter at every possible location and get the same sized image. So what is the fundamental difference now? So this is the signal processing I wanted to check out, and this is based on some theory. In physical systems also, there is a class of systems called linear time invariant systems, whose something called zero state response, right? Zero state response of a linear time invariant system is just the convolution of the input and the output. It could be in 2D, 3D, 4D, and so on. Right? That theory is well established, but we are not going into that detail. But what we are trying to do is we are trying to get that theory, which is quite useful, right? So, and in this example, you tell me how many inner products you will do. The number of inner products you do with this filter, always this second sequence here, the second matrix, we call it a filter, and the first matrix has a data or signal. So how many other possible locations you can keep this center and take an inner product, right, with the original thing. Normally whatever is the data, that many, how many points are there in the data matrix or this X1 matrix, that many other possible locations, we will make sure we keep that and take in that many inner products, so that the final 2D data, here you can call it an image also, image is a 2D data. So that also has, it's a grayscale image you can assume. So that also has that many number of bands as the original image. Everyone got it? Everyone understood what is this convolution? Now in a 3D, what you will do? You can assume this data as a cube or a cuboid, and then the filter as a cube, small cube or a cuboid, and all the possible locations you will penetrate and move it around, right? And then get how many ever inner product, that would be the output thing. So we are going to use this thing, to count the number of channels and number of filters, right? And everything in a CNN. Okay. So this is the basic thing. So what is the fundamental difference? Anyone, can you tell me now what is so special about deep learning and what is the classical thing? Classical thing also people were doing this. So given an image, which is a 2D thing, they used to design a filter and then move it around. So one example of a filter. So suppose you want to detect the edges in the image, right? Let's assume this X1 is the image and X2 is the filter you want to use to detect all the vertical and horizontal edges in the image. So vertical edge is something formed by this pencil, if I keep it like this. Horizontal edge is the pen, this one, right? So you want to form it. So one is an operator called, I think, Sobel or Prewitt operator, people used to call them. So it's this thing, I think this Sobel operator and Prewitt operator. There are two operators. So one of them I will write down the X2 matrix for one of them, because X1 could be any image coming. Whatever image comes in, I want to detect the horizontal edge and the vertical edge, right? So you would use two matrices and convolve them. One matrix will detect all the horizontal edges and another matrix will detect all the vertical edges. The operation is convolutional. So keep that matrix I'm going to write down at all the possible points in the image and take that many inner products and output the image. Okay. So this one, I can say it to be -1, -2, -1, 0, 0, 0, 1, 2, 1. Okay. This will detect all the horizontal edges, because it's, if you observe it closely, what it is doing is it's taking some finite difference, right? Finite difference in this direction. Finite difference is an approximation of derivative. So derivative will find out the rate of change. That is what the edge is, right? So you have some sudden change in the intensity values. Okay. So another thing I will write down for vertical edge. So you need to just transpose this. So these things you use. But now, having given this example, can someone guess what is the deep learning? Learn these filters. Yeah, he is correct. So here I am specifying, I am already saying like for vertical edge, I will use this filter. For horizontal edge, I will use this filter. So in deep learning, you will initialize all the filters to some random things. So it will automatically learn it. So that's why there is one new name which is popular for this class of deep learning kind of algorithms. It's a representation learning, right? So because what is the thing? So you have a CNN which we are going to see. The first few layers act as some kind of filters to process the input raw data, which could be useful for the later layers. Right? So edges and all these corners, everything are detected in the first few convolution layers. And later convolution layers do some higher level vision. So I told that all the problems of vision which are not involving recognition, they call it mid-level or low-level vision problem. So we can say that CNN, first few layers are doing the low-level or mid-level tasks necessary for it to do a high-level task like recognition at the end. So an example is this ImageNet challenge. All the major CNNs were developed to do best in that ImageNet challenge, right? So all of them, if you take out the activation maps from the first few layers, you will not get any category information. You will get some edges and all the low level information. So that people have shown it also. Okay. So this filter, what are the values I want to put here, I already pre-decided. Okay. So the people, the deep learning community, they call it engineered. So I am already engineering, right? So engineered features. So if I already use it and take out the edges and then give it to a learning algorithm, I am using engineered features for the algorithm. I am not learning the feature. Yeah. No, that image itself goes. That's what we are going to see. So we'll go to the architectures from the primitive to the higher one, right? From LeanNet, we will start and do it. And then okay. So we are going to stack those images as a number of channels and then design another filter. We are going to specify what should be the output. So we are only concerned about input dimension and output dimension. The filters are learned in the process. All are, you don't call them images anymore, but you call as tensors. It could be a 2D tensor or a 3D or 4D or so. So image means something it should visually convey, but after that it loses that significance. But we will visualize and show you some of the things from the popular networks. Okay, everyone clear with this? So one more thing I wanted to cover is this thing. So someone told matrix. So everyone clear that the convolution is just a chain of inner products. So how many inner products? What is the dimension of the output? That many inner products you have to take. Yes, each inner product gives you one value for the output. The same concept applies to CNNs also. Fine. So next thing, so this geometry, let me talk about this camera matrix, and it could be useful when you solve some of the applications. So this camera matrix in vision, what you do is, so I'm not going to derive the camera matrix or anything. I want to tell you, so how complicated the challenges in recognition are. Because we are losing one dimension. So you need to know the amount of compression it is doing for us, right? So how much one dimension, throwing away one dimension, how it affects the data itself, right? So there are many challenges. One of the thing is you want to make predictions of the 3D world only with 2D data. That's a main challenge. So where that one dimension is gone? To answer that, we need to understand what is the camera matrix. Okay, so what is a camera matrix? So in the projective geometry, what we will do is any 3D point which is infinity, right? Finite 3D point, there is something called infinite 3D point. Finite 3D point, we append a 1 to it. If it's a 3D coordinate, X, Y, Z. So any point here in 3D, I want to specify, I will give the coordinate X coordinate, Y coordinate, Z coordinate. I will add one to it. But I take a camera here. Always we are going to assume in projective geometry, the camera is a pinhole camera. Pinhole means there is no blur. Only one ray comes and it hits. So there is no defocus blur. So wherever I keep the image plane, I will change the magnification, but I will cut across the rays and there will not be any blur. Okay. So that is the assumption we are going to make. So for a pinhole camera, if I have a 3D point, XYZ given to me, I'm going to append one to it. And wherever it is captured in the image, if it is in the point, if it's a finite point, I'm going to add one to it also, XY1. Always I want to have it in XY1 location. If it is not in XY1 location, I will divide the X and Y by the last entity to make it one. So if it is XY some K, so then I will, that is equivalent to X by K, Y by K 1. Okay, this much if you understand, that's fine. So now let's write down the camera matrix. So camera matrix, so any 2D point in the image, okay, is related to a 3D point. I'll use a different X, Y, Z for both through this camera matrix. That is the reduction which is happening. Okay. This camera matrix has two types of parameters. If you want to go in detail, there is a extrinsic parameters which capture where my camera is located, what orientation it is, and there are intrinsic parameters like focal length, right, and form factor and many other things. We don't want to go into that. This much is enough. So every image point, this is the 2D, and this is a 3D. So this is the image, and this is the world. The main challenge comes in this inference problems or the recognition and the other kind of problems in computer vision is the fact that we are only observing the image, right? One dimension is gone. We want to make predictions on the world, which is a 3D world, right? So that's why some people ask also why these deep learning models are very data hungry. So now there are methods which can work with a limited amount of data, but you need to show so many examples for it to predict the 3D world with only the 2D projections of it. So some people call it why this thing is called P, it is also called a projection matrix. Okay. And if you have two images in two constraint settings, if you want to relate two images, when I don't want to go to 3D, right? When I don't want to go to 3D, if I want to relate two images, what is happening in two images? If I don't want to go to 3D, two settings, it is possible. We can relate coordinates in one image with another image through a single 3x3 matrix, because I'm telling the 2D thing would be 3-dimensional. So I need a 3x3 matrix to go from the one representation in 2D space to another representation in 2D space, right? One setting, let's not worry about the derivation and everything. One setting is the typical case of this, you might have seen that CCTV cameras. So what it can do? It can pan, it can tilt, and it can zoom. The PTZ cameras. And the scene could be anything. It could be dynamic. Still, if you have a PTZ camera kind of setup, you take two images. So one with some pan, tilt, and zoom, and next with different pan, tilt, and zoom. Then they could be related by only a single matrix. Two images could be related. We don't have to go to the 3D to relate those two images. So another setting is if you have so pan tilt camera doesn't move. There is no translation, right? Because it's fixed. So it can just pan, or it can tilt, or it can zoom, right? These are the operations. It cannot physically move, or the camera center has not moved. I can say that pinhole, this thing we said, that is a camera center that has not moved or translated. But the translation is allowed if it is a planar scene. Then also the same matrix will relate two images. Suppose I don't want to capture anything else. I have this bench near me, which is a planar thing. There is no, the depth variation is very smooth. So I take one image of only that section like this. I move here, take another photo, right, of this planar thing or this table for an example. I take one, right, and then move and take another. Those two images I want to relate, right? Then what I can do is I can use the same thing. So suppose the coordinates in the second image, I denote it as x dash, y dash 1, and I can have a 3x3 matrix which relates the coordinates of the first image. So this is the image 1 coordinate. So every image 1 coordinate is related to image 2 coordinate using a single 3x3 matrix. This is also called a homography matrix. Okay. So the other one is projection matrix. This is a homography matrix. Okay. This we are moving to the two view setting. So two things. But in general thing, we cannot have this constraint, right? So we cannot have like the scene should be planar if you move the camera. If the scene is not planar, it has a lot of depth variations. The scene has a lot of depth variations. Then you should have what you should have. You should have only pan, tilt, zoom motion. So the objects are also moving, then some complexities arises. We don't want to worry about it. Let's consider static scene. If there is no depth variation, it's a planar scene, then you can move the camera to two different things and relate those things, right? But so this is the complexity involved. So now then people started developing for both the cases. So scene depth also can vary in whatever way it forms. It may not be planar. It could be a lot of variations. And also the camera position also could be anywhere, right? So that led to this epipolar geometry, which is the two camera setting. Okay. And the extension of this epipolar geometry to n or more camera, there is another theory, which is the structure from motion. Everyone understood these settings? So you have multiple images, so they could be captured of a static scene we are assuming. So they could be captured with camera at one position and camera at other position. So the depth variations you want to capture, right? So much geometry has gone in actually to create the scene of different things. But one thing, whether you like it or not, which made this deep learning powerful is many of the deep learning algorithms or the network architectures are agnostic to what the geometry was between that. Because the thing is, you need to make the model like robust enough to understand various settings. So you show more examples or do some tricks in the model itself to capture the variations. So it doesn't need to go right and look at. So for an example, if you so let me take a very practical example to emphasize this point. So suppose there is a image of a fast moving vehicle. So now let us introduce motion in the scene. So some car is moving. So you would have encountered also. You click a picture of a fast moving object. Your shutter time, right, is more than the speed of the vehicle is so much. Your longer shutter speed, right? That then what happens? Motion blur will come because many 3D points are contributing to a single point in your image. Because you are letting more rays from different 3D points into the same point in the image because the object has moved. That's the reason of motion blur. So traditionally, what people used to do, they wanted to undo the process. So that's also a process of convolution only. So there is a like spatially varying blur, you call it. Blur means something has convolved with. So image has to be sharp, but because of the fast motion of the vehicle, some kind of blur has been introduced. So blur means the convolution which is happening, it's a low pass filter. So it has removed the high frequency details, which are the details you want. For an example, number plate may not be visible. The number plate has sharp edges and everything, which is a high frequency component. But this convolution kernel, the nature or the physical system had a convolution kernel which was enforced on the camera to make it look doing a low pass filtering operation. That's why you got the blur. So the traditional way is to estimate the blur at every pixel. What is the blur kernel? Then you do need to do the deconvolution. So you need to undo the convolution. So you need to do a deconvolution process. So you will get the clean image. From the blurred image, you will get the clean image. So the classical people were trying to do that. Some of the learning algorithms earlier was, but with the advent of GAN, the generative adversarial network, in 2014 by Goodfellow and others, right? So what it enabled researchers, one of our works also there, many people have done similar things. So given a blurred image, you can deblur it without even estimating that blur kernel or the convolution process. So how the convolution process happened, that you don't have to know. So it's an end-to-end learning. Give a blurred image, the GAN will synthesize a clean image. So it freed up. So you don't have to understand the physical process which is happening. That's what I told you. Right? And another thing, even the homography also, there are some deep learning methods where you feed in two images. It will give you a matrix which relates this H3x3 matrix, which relates every pixel in one image to every pixel in another image. So if indeed the photos have been captured in the two settings I mentioned, pan tilt zoom with any variation in depth or translational motion between the two images of a planar scene, if the photos have been captured in these constraint settings, the homography matrix you estimated using deep learning, this thing. So what the deep network will take is, it will take two images and output a homography matrix, 3x3 matrix. So use the 3x3 matrix you estimated on and multiply all the pixels coordinates in one image, transfer the intensities, you will be exactly be able to reconstruct the second image. Given the capture process, you followed either of those constraints I mentioned. This is the power. So you don't have to, like, you can verify also. So you want to have a check, right? Yeah. Which one? No. Camera could be in any position. Actually. Yeah. I can capture one thing like this and one thing like this. But the part of the scene which is common to both the cameras, this homography matrix will be obeyed. Common part. So there will be some out of field of view, common field of view in both the cameras, it will obey. But there may be something because of the position in which you captured, some may not have a proper correspondence in the other image. So there may be a non-planar part also, right? They may not obey. So whichever is the planar region that will obey, but it should have a correspondence in the other image. The 3D scene common to both the camera views will obey. Okay. So any questions? So I thought I have been able to give you a flavor, right? So how this deep learning? So why this deep learning thing is powerful, right? So why this deep learning is powerful and why computer vision people? So one thing is the inference time, right? So another thing I am going to introduce. So this is about the classical thing. The inference time is very fast in the deep learning. Right. So let me come to the next thing, next topic I wanted to discuss. We have another 15 minutes. We will go into the learning based vision. So there are two paradigms. So one people, what they were doing was they were having an image or video. You have to manually extract or engineer the feature and give it to a learning algorithm. Then only the learning algorithm will work. That was the classical machine learning algorithm, like SVM, random forest, right? What other classifier you know? Logistic regression. Then K nearest neighbor. All those things will not take the raw data. What you need to do, given an image, you want to do this recognition tasks. So you need to, the user has to extract the feature. Then there was one group who were trying to create more and more powerful, discriminative, and distinctive features. So the feature extractor should extract something distinctive about the image and discriminative with respect to other images, so that this feature vector itself is very powerful. You feed it through this learning algorithm, the half the job is done. The SVM and this random forest, they will just random forest, it will do the bagging, boosting, all those algorithms will do the job and do the final thing. But that is one thing, which is a classical machine learning. The deep learning thing is end-to-end learning. So why do you call this end-to-end learning? The feature extraction is never done. So you feed in the raw data, finally you get the prediction or the recognition, right? So suppose I want to classify this learning in vision, I can draw two diagrams, which would help you understand what we are getting to. So we are not going to discuss at all the first thing, because it has become obsolete. But from the historical perspective, you need to understand that. Okay. So the first thing, what it does is, let's take a image recognition problem, like ImageNet kind of thing. So what you need to do, you need to feed in the image so let us take this image recognition. So given an image, it needs to tell what out of some 1,000 categories, what category is present in that image. Okay. So image is the input and output is the prediction of category. Okay. So a bit below. And the first thing is the classical, here also classical machine learning. Okay. So we understood the difference between classical computer vision and the learning based computer vision earlier. Now we are going to understand the difference between classical machine learning and the deep learning. Okay. The classical machine learning requires you to have something called feature extractor. So this will give you a feature vector which is fed to this ML algorithm, which could be this SVM or logistic regression or trees, forests, etc. And finally, the prediction will happen. Okay. So you understand. So the learning process involves. So first time, what you will do is you will keep showing the image with the correct category every now and then. There will be a loss function. Again, you will train that model and do it. This feature extractor, this is also called by this new deep learning people as engineered, as being engineered. Yes, there is a disconnect between the ML algorithm and this one. So finally, you want to say your results. You have the luxury to, if some feature extractor doesn't work, you throw it away. You get a new feature extractor, put it in my box, and improve the performance. So that's why it is engineered. So there is a manual thing involved. So though you think that feature extractor can just like that get the feature extractor, but what feature extractor to use, you have the luxury to specify. So I need this feature extractor. So this is not working, so I throw it away. So I put this. So there is thousands of different feature extractors, local descriptors were this thing. So some of the extractors, example in literature, which are very famous, are SIFT, you can think of, serve, and some combination of this feature is then fed to the ML algorithm. Serve, then ORB, right? And Kaze, many such things. Okay, some of them are in OpenCV also, and MATLAB you can find. Okay, so the onus is on you to extract the feature. So the feature extractor, what it comprises of? It comprises of a lot of convolutions and other things again. Okay, for an example, SIFT has a lot of some kind of filters called LOG filter, Laplacian of Gaussian filter, whose coefficients are already hard coded there. So it's not like this descriptor is also learning. The descriptor is fixed. It means all the components in this feature extractor are engineered. So you already freeze those things. So a lot of convolutions happen. So for an example, SIFT has a lot of Laplacian of Gaussian filters, whose coefficients you already know. SURF has a lot of wavelet, Haar wavelet based filters, whose coefficients also you already know. ORB has something like this. Okay, so you can find out. Okay, different things whose coefficients are already hard coded. So it is not learning. Everyone understood? Okay, so but these two things got combined. So the end-to-end learning, we call it, because this deep learning merges these two blocks, like it connects to what I told earlier also. First few layers of your deep CNN act as feature extractor for the later few layers. And the first few layers also, so you do a back propagation and keep doing it again and again. The weights of all the layers from first layer to the last layer gets changed. Right? So in the deep learning, I can write as why it is called end-to-end. Some people call it black box, but it's convenient for us, right? So because you have this guy, deep learning algo, and you have a network, and this is an image, and finally you get the predicted category directly. That's the entire thing. So the image is the input and predicted category is the output. So you don't extract the features separately. So how does it help? Because you are learning this thing through the back propagation. The training time is quite high for the deep learning, but that's why it has been speeded up due to the advent of the GPUs, because you can parallelly learn multiple weights at the time. The training time is quite high, but that has been speeded up through the GPUs. But the inference time, for this feature extractor, a lot of convolution and many things you need to do internally. So for the image, when training as well as testing, this feature extractor is a hard-coded block, I told, right? So it needs to do the same processing, right? But in the deep learning thing, in the inference stage or in the testing stage, you are going to do only one forward pass. You're going to do a lot of matrix multiplications and some non-linearities you are going to do. Right? So that way, in the inference time, and also they can be done also in parallel, a lot of them. So this deep learning algorithm in the inference time is much faster. And the functioning of this ML algorithm in the accuracy, final accuracy, depends on this feature extractor, which is hard coded. So if this guy starts misbehaving after some point for some images of some different classes which have not been seen, so already you have reported everything with this feature extractor. Again, retraining for all categories, replacing this feature extractor with something. So this guy is not performing, I'll put this. Yeah. Yeah. Not really. We are giving the raw image only, right? So just specifying the number of dimensions of the things, right? Dimension of the filters you are specifying, but not what the content of the filter is. Huh? Yeah, that is up to the user. So that, yeah, that is a good question actually. So, but it's like a gentlemanly agreement. So some of the questions no one asks and no one answers. So like for an example, why 7 layers? Why not 10 layers? And why this many filters? Why not this many filters? I have never found any answers to it. So I also got it. But so those things, like, because they were people use it, so something like that. So normally people justify. So most of the deep learning thing, how you justify also, right? So that it's a valid question. So what you do is we don't like why this many, that no one asks. But what they see is at a very black box level, every component in the deep network is important. So every method, what it does is, for a full network, they report a performance. Then you want to show that everything is useful, not at the level of number of filters and all, but some new component you put. So you remove it and show that the performance decreases, and remove another component from the full complete deep network and show that the performance reduces, right? And then you prove that every bunch of component in the deep network is necessary to get the highest accuracy. So this study is very common. You can see in many of the papers. It's called ablation study. So that is the gentlemanly kind of notion people have agreed, in the sense that, so the ablation study is thorough, that tells that all the components of the nature are necessary for my best accuracy. So that's how the field has been moving. But his question at the primitive level, why this is the dimension of the filter, why this many filters. So those things is left to the everyone. Whoever reads can understand or ask or try out different sizes and different number of filters and see that this thing, right? So, but yeah, that's how it is. Because some of the networks are trained for days and months, so no one has the time to change those and this thing. So always this. Yeah. That's correct. Yeah, what he's saying is correct, but yeah, that needs to be explored more actually. But people go with the kind of study they do. So build a complete network, remove every component, and show that performance decreases. So every component is required. So that's at the black box level. It's not at the ablation study is never done at the filter size level or number of filter level and so on. So hope everyone understood, right? So this is the approach. So we are not going to consider from tomorrow's class onwards the classical vision also. We used it to understand the class of problems, the vision, and why it is difficult, right? So one more thing I wanted to tell is this radiometry or photometry based thing. Why they are useful is even the images could be captured in different lighting, right? So in the classical vision sense, like you cannot, if you don't train a model, if you show a slightly variant lighting, it may fail actually. But the deep learning thing, you can also do something called data augmentation by varying the different rotations and everything. So you try to synthesize artificial data and mimic it. So normally it does far better. So most of the things nowadays, almost all the computation problems have the top performers are deep learning methods. So we are not going to do this. We are going to focus on this. And what we are going to do is we are going to have this prediction category is a inference kind of problem, right? So it's a recognition kind of problem. So another problem we are going to see is synthesis kind of problem, when there is an image as input and image as the output, or some information as the input and image as the output. So generative things we'll see in one session, and the inference thing in another session. So any doubts you have, anyone? Or we can take some doubts. So you can read up the resources I gave, and if you have some doubts, you can ask. So now the basics I have covered, and you have understood this convolution. I think we can go further tomorrow. Okay. Thank you, everyone. Let's wind up the session.